What does a generational technology dividend actually imply in the hardware space? And second, based on industry movements, what are these four converging pillars they are keeping off the record?
Well, this raises an important question about the term dividend itself. In finance, a dividend is a compounding payout from a long-term investment, right?
Right. You invest early, it pays off later.
Exactly. So in deep tech hardware, a technology dividend is a massive structural payoff resulting from years, sometimes over a decade of deeply funded prior R&D. It means the breakthrough isn't just some iterative percentage increase, it completely obsoletes the previous tier of capability.
So it's basically the harvest of seeds planted 10 years ago.
Precisely. And to fill in the blanks of Old Peng's cliffhanger, if we look at the TSMC and NVIDIA engineering roadmaps pointing toward 2028, those four converging dividends become glaringly obvious.
Okay, let's hear them.
Pillar 1 is directly tied to the CoPoHES packaging we just discussed. It's the transition to glass substrates.
Okay, let's visualize this for a second. The industry has traditionally manufactured chips on circular silicon wafers. Using a circular wafer to cut out rectangular chips is, it's like baking a circular pizza and trying to cut it into perfect squares.
You end up with a lot of wasted crust.
Exactly, a massive amount of wasted crust around the edges. By shifting to rectangular glass panels for the substrate, you jump to over 95% area utilization. It's like baking your pizza on a giant rectangular sheet pan instead. You maximize the usable space.
That's a great analogy. The geometry is definitely one factor, but the physics of glass is the real dividend here.
How so?
Current organic substrates suffer from a high coefficient of thermal expansion, or CTE. When a massive AI chip gets hot, the silicon die and the organic substrate beneath it expand at completely different rates.
Oh, I see. So they push against each other.
Right. And this causes the entire package to warp physically. Glass substrates, on the other hand, have an ultra-low CTE that closely matches silicon. It provides near-zero warping, even at extreme temperatures.
Wow.
And because of that stability, it allows TSMC to expand the chip package to roughly 9.5 times the traditional reticle limit.
9.5 times. That is huge. And I guess that sets the stage for pillar 2. We have this massive, stable glass panel, but we still have to get data in and out of it, right?
Exactly.
And that brings us to co-packaged optics, or CPO. Up until now, data centers have basically relied on highly complex 78-layer copper-printed circuit boards to network these AI racks together.
And we are really hitting the physical limits of copper. When you try to push high-frequency electrical signals through copper over any meaningful distance, you experience severe signal degradation and attenuation.
So they just lose juice along the way.
Exactly. To compensate for that, you have to pump massive amounts of power into the system just to force the electrons through the metal. And that generates immense heat. Copper PCBs are basically a dead end for next-generation AI clusters.
So the dividend here is replacing electrons with photons.
Yes, moving to light.
Shifting to co-packaged optics means integrating silicon photonics directly onto that CoPoS package. Instead of routing electrical signals through a copper motherboard to a separate optical transceiver, the chip itself converts the data into light and fires it out through fiber optics.
And the bandwidth implications of that are staggering. By utilizing co-packaged optics, NVIDIA can bypass the copper bottlenecks entirely. Currently, they can network a rack of 72 GPUs, known as the NVL72, using traditional copper switches.
Right, which is already a beast.
It is. But with CPO on the Feynman architecture, they can daisy-chain these racks into massive optical clusters. Think NVL576 or even NVL1152 setups.
So 1152 GPUs acting as one.
Operating as one unified, giant GPU with virtually no communication delay across the entire data center.
That is mind-bending. Which brings us to pillar 3, and this deals with how the chip accesses its memory. It is called 3D stacked SRAM via hybrid bonding.
Yes, a very critical piece of the puzzle.
If you look at the specialized AI startups out there, companies building LPUs or language processing units, their entire competitive pitch relies on overcoming what they call the memory wall. They argue that traditional GPUs waste way too much time fetching data from separate memory modules, which creates huge latency when you're trying to run real-time AI agents.
And to be fair, the LPU startups have a very valid critique of current architectures. If the logic processor has to constantly pause its calculations just to wait for data to arrive from external memory, overall performance plummets.
Right.
This is where 3D stacked SRAM completely neutralizes that startup threat. We've seen early iterations of this concept with AMD's 3D V-Cache, but Feynman takes it to the absolute extreme.
Okay, so by utilizing hybrid bonding, they are taking massive banks of ultra-fast RAM memory and basically stacking them directly on top of the logic dies, like physically fusing them together at a microscopic level.
Right on top.
So the data doesn't have to travel across the circuit board. It literally just drops straight down into the processor.
Exactly. The latency drops to near zero, which completely obliterates the specific advantage those LPU architectures claim to have.
It just wipes them off the map, which leaves us with the fourth and final dividend. This is TSMC's A16 process node and backside power delivery.
Yeah, the A16 process represents the leap into the 1.6 nanometer class of transistor density. That is shrinking the logic gates down to near atomic levels. But shrinking the transistors creates an absolute nightmare for routing power to them.
Think of a chip design like building a skyscraper,
Yeah.
right? Traditionally, all the messy plumbing, the electrical conduits, the HVAC ducts, they all have to be routed through the exact same floors and hallways where the people are actually trying to live and work.
It gets crowded fast.
Exactly. On a chip, the power lines and the data signal lines are all woven together on the front side of the silicon. It causes massive routing congestion, and the power lines actually physically interfere with the data signals.
Right.
But backside power delivery, or BPD, changes the architecture completely. It's like taking all the plumbing and utilities out of the living spaces and hiding them strictly in the basement or the structural core of the building.
The engineering elegance of BPD is honestly remarkable. They route the entire power distribution network completely to the back of the wafer, feeding the transistors from underneath.
This means the front side.
This frees up the entire front side of the chip exclusively for signal routing. The result is a drastic reduction in power loss, significantly lower operating temperatures, and it allows them to pack the transistors much, much closer together because the power lines are no longer in the way.
Wow. Okay, so let's look at the real aha moment here. Old Peng didn't just say they had a technology dividend. He heavily emphasized a perfect convergence of four of them.
Yes.
Competitors in the hardware space can often reverse engineer or copy a single breakthrough, right? If you figure out backside power delivery, someone else will eventually figure it out too.
Sure, but the mathematical reality is that compounding advantages are nearly impossible to catch up to. Combining four distinct generational leaps into a single launch, meaning the Feynman logic built on the A16 node with backside power, vertically stacked with 3D SRAM, utilizing co-packaged optics, all sitting on a Copas glass substrate.
It's an unprecedented convergence.
Unprecedented.
It is the equivalent of the original iPhone launch, where the multi-touch screen, the internet communicator, and the iPod didn't just launch in the same year. They converged into a single device that reset the entire industry standard. If NVIDIA truly aligns these four monumental hardware breakthroughs to hit the market simultaneously in 2028, it renders everything prior completely obsolete.
And that perfectly explains their willingness to absorb hits and take a defensive posture with Rubin Ultra in 2027.
Right.
You do not risk leaking or prematurely launching one of those individual dividends if the true industry-breaking power comes entirely from how all four interact together on that massive glass panel.